Easibex is an easy mean to use Ibex. It has been developed at Bretagne by mainly Fabrice Lebars and Jérémy Nicolas. And this tool makes it possible to use easily Ibex for contractor programming. To use Ibex, you need to have strong notion on C++, such as object programming. Now most of the engineers and researchers use MATLAB or Python or other high-level programming languages. And if they want to use Ibex, with Easibex, it is much more easy, as we will see later. To draw boxes, which is classical when we use interval arithmetic algorithm, Easibex use the Vibes, which is a tool, API tool, which allows us to draw easily boxes. Here you have some papers to understand what is contractor programming. And now we will focus our attention to how we can use Easibex with C++ Qt. So we can download here a zip file and this zip file will make it possible to use Easibex in a Qt C++ environment. So here you have a light Qt C++, which is sufficient. You can download it via this link. So here is the address where you can find Easibex. So in my computer, I have already installed Qt C++. So exactly this one. And if I click here to download Easibex for C++, and I record it. Okay. So it takes something like 1 minute. I will stop it now. After I unzip this file, and then I will obtain something like this. Once I have unzipped all, I have Ibex here, which is already compiled, so I will not see what I have inside. Here I have some other tool, Soplex, for linear resolution, a README. Okay, just to explain that it will compile perfectly with Windows. But what I really need is the Civia, the Qt project. So in this Qt project, I have Vibes, we'll see later, which makes it possible to draw easily boxes. And I have the project, so civia.pro, and this will run the program, the Civia algorithm. Here I have my project, the header, and the source file. Header, source files. The main program is here. I have here is the Civia algorithm with some Vibes statements. For the initialization, I include Vibes, of course, the interval and the box library. Also the list in order to manipulate lists. I will start by running this simple program. So it compiles everything. It will take maybe a few seconds. So it starts here and I can see nothing. So it is normal. I will now explain why. first to start vibes. So vibes, we'll see, it is a small exe file, and my program will communicate with vibes in order to draw boxes. So I come back here. If I run it once more, I can see here the picture which corresponds to what the program gives me. So this program draws a paving. I can zoom in, I can move here. So this is what does vibes. And I have a lot of boxes. So blue boxes are outside, red boxes are inside, and yellow boxes are cover the boundary of the set I want to characterize. So vibes is an easy way because it's easy to draw. And then after, I can move and I can also draw and see what happened during the execution of the algorithm. So then I stop this, but I do not close vibes. So now I will try to explain what happened here. I have an initial box, and I will call my contractors. In order to understand this program, I will consider a much more easy example. I will avoid to take two contractors, but I will consider only one. And this contractor will be taken in the list of the elementary contractor I have in my library. So if I look at intervals, I have plenty of contractors, and a simple one is this one, for instance, associated with the sine function. So here I will do this. I will consider x of 2, which takes the role of y, and here x of 1. If I run this program, so I have only one contractor, which is this one, and I start it. The result is here. And my function sine appears. So I will explain maybe here how it works. I have here my sine function, so I will draw it. And my sine function is like this. And what is the contractor C sine? So it takes as an input a box, let's say this box, and it will return as an output this box. This box. So here I have the contracted box C of x, whereas the initial box is this one, x. So as we can see, no red point has been removed by the contractor. What happened is in the CV algorithm, once the box has been contracted, if it is large enough, then I will bisect it. So if if I bisect this box, I will obtain this green box and this other green box. Okay. If I continue this, I will obtain such a picture. What does the CV algorithm? Okay, I can zoom and I can see here my yellow boxes. Of course, Ibex is a tool which makes all possible to build easily the primitive contractor, such as this one. Very simple. So here I use Ibex, but I can also build much more complex contractors using contractor programming. Or here, for instance, if I use tangent, I will obtain this. Okay. Assume now that I want to solve a system with two unknowns and two equations. Say x2 equal tangent of x1 and x2 is equal to cos of x1. So to do this, I will build first a contractor for this one, C1, and then a contractor for C2. And this corresponds, this first constraint, this one corresponds to the set of all x1, x2, which satisfies this equation. And the same for the second equation. So if I have this set and this set, I can do the intersection. And if I do this, I will solve these two equations. But I can also do the union. And if I do this, I will represent the set of x1, x2, which satisfy either the first equation or the second equation. So I will illustrate this with Easibex. I have my CV algorithm, and my CV algorithm calls here one contractor, Cout. So to do this, what I will do, I will build a box, A, which is equal to X, and the same box B, which corresponds to X. Then I will contract A with respect to the first equation, and a contractor associated with the second equation. So the one is applied to A and to B. Then I will do X equal, so if I want to do the box union between A and B, and if I do this, I will represent the union of the two sets. So I will do this now. This is the result. I have here a picture of the union of the two sets, the one corresponding to the tangent function and the other one to the cosine function. If I want to now draw to solve the system of equation, I will have to do the intersection. The intersection is done like this. I do the intersection between the two boxes. I run it. And here, all yellow boxes here, so this is the yellow boxes, contains the solution. So all solutions are enclosed in the yellow boxes. Easibex encloses a lot of contractors in interval.cpp, and most of them use Ibex, are built with Ibex. So for instance, this contractor is related to a circle. So let me use it. Take this one, and we can see that this contractor is built as follows. First, we build some variables for Ibex. We write the constraint in a symbolic way, which is interpreted by Ibex, which builds the constraint with respect to these variables. Then we have some technical details that we do not need to know when we use Easibex. For instance, the contractor is related to the algorithm HC4 revise, which is a forward-backward contractor. Then there is some try and catch to consider the case where I have an empty box. But we do not need to know this kind of syntax except if we want to build our own contractors. But we can copy this one, for instance. I come back to the main and I will replace this by, I will call, for instance, contractor with respect to a circle. Here I will have x of 1, x of 2. The center of the circle, for instance, will be 2. Here it will be 3. And the radius, let's say, 4. If I call these contractors, I run it. Okay, compiled, now it's finished. I can see the circle with the corresponding radius, and also the circle with the yellow boxes, which are here very teeny. Okay. When we want to characterize sets with Civia, so for instance, consider here a set X, we need an inner approximation and an outer approximation. So if we start with a box like this one, the inner approximation will give you the outer approximation will provide you a box like this one. I mean, this all this part has been removed. Okay, so outer contractor, which are called most of the time here, so here it is a box X, and the contracted box is C out of X, only remove parts that do not belong to X. You also have the notion of inner contractor. So here you have a box, and you will only remove part of the box that are inside X. So it means that this has been removed. So here I have the box X, and here this box corresponds to C in of X. So most of the time we need to deal with the inner contractor and the outer contractor. So if we have a specific tool or object that manipulate both together, which is called a separator. So if you want, a separator is a pair of two contractors that are complementary. an inner contractor and an outer contractor. Easibex contains some separators. So most of the time it starts with S. It is like a contractor, but you have a Boolean value, which is called here outer. When outer is equal to 1, it is a classical contractor. And when it is equal to 0, it is an inner contractor. Or it is easy to use, and I will show in this example how it works. I use here, take here, I take again this contractor. Here I will put 1. The radius will be, let's say for instance, 1, 2. Here I will have 1, 2, it is the center. Here I will have x of 1. Here x of 2. And this corresponds, so if I want a specific drawing here, this contractor is associated to a set which has this shape. This shape. Okay, and this part is inside the set. So what I have programmed just now, it is a contractor which takes as input a box and which will return such a box. It may be smaller, maybe if it is optimal, maybe in this case it will be less. Okay, so only the outer contractor at the moment. So let me come back here. I start it. There is an error. Okay, this. What happened here? Here there is a problem of time because there is so many boxes, because I have only the outer contractor. Inside I have plenty of boxes because I miss an inner contractor. Okay, so in order to do this, that's what happens when we want to characterize sets with an inner and an outer approximation. So what I need, in fact, is stop this. What I need is also an inner contractor. So I take exactly the same in, but here I put 0. So it is why it is interesting to have a separator, because we have the same function to call. In the CV algorithm, what happens now? I draw the box blue and I contract it. I will do the same. I will draw it red. Then I will contract it by the inner contractor. I run it. And this is exactly the ring you wanted to obtain. So it is why it's interesting to have the notion of separators. And most of the time when we want to characterize sets with volume, we have an inner contractor and an outer contractor. So now to finish, I will consider a problem of localization of one robot with a range-only measurements. So I have a landmark here, which coordinates, let's say, 1, 2, and another landmark, let's say, for instance, in here, and with coordinate, say, 2, 5. So I can also draw here my axis. And I have one robot somewhere. But I don't know where is this robot. So let's say, for instance, it is here. I am able to measure some distances. So let's say, for instance, these distances and this distance. So the distance d1 and d2. But I always have some errors. So say, for instance, that I can represent this error by an interval. It means that d1 belongs to the interval, say, 4, 5, and d2, for instance, to the distance 5, 6. Now, where is my robot? So each measurement, for instance, this measurement will correspond to a contractor, say, C2, whereas this one will correspond to the contractor C1. And I will build the contractor for C1 intersected by C2, but also so an outer contractor and an inner contractor for C1, C2. So C1 corresponds to the set S1 of the set of all positions for the robot which are consistent with my first measurement, and this contractor will be associated to the set C2. So of course, to build, I want to characterize C1 intersected by S2. And for the inner contractor, I will have to use the De Morgan rule. So I explain it now, so it will be more easy to understand later. The complementary of this is equal to C1 complementary union S2 complementary. This is the De Morgan rule. Okay, so for the inner contractor, we'll have to use this property. I will illustrate now by a program. So here I will have interval of 4, 5 for the first one, but I have also for the second contractor 2, 5. This is the coordinate of the landmark, and here 5 and 6. Thus, I will not use any inner contractor. So I will take a small precision here to avoid takes too many time, because there is no inner contractor. So in the interior of the intersection of the two sets, it will take time. So let me run this program. I have it represented here. This is my solution, but I have no inner part, so that's what it takes time inside. Okay. Now, here I take this, but to build another way to do this is the following. So we'll understand later why it is important to act like this. Box A of x box A B of x, I intersected A like this, B like this, and I will say that x equal to A intersected by B. So it's the same. If I run it once more, I will obtain something which is similar. So I have, look here, it is similar. Now, if I do the same for the inner contractor, I will do this like this. Oh, so it's the same. But here I take the union because of the De Morgan rule. If I do this, 0 here, of course. If I do this, I will obtain the same, but with much less boxes. So it takes less time. The last step I want to illustrate is instead of building each time an inner and an outer contractor, which are quite similar, it is often much more accurate, much more easy to use the concept of contractor, of separator, excuse me. So let me here consider a separator. Separator with bool outer, so I need this one. Here I call outer, here outer, and if outer, I do this, else I do this. So, of course, for this simple example, this is my separator, and here I will call my separator with 1, and here my separator with 0. I compile, and I will obtain a similar result. So, of course, for this simple example, the number of lines of code is not totally different, but when we combine, when we have more complex situation, it can help to have more simple programs.